Okay, so today we're going to start off our next unit by looking at probability. And probability is something we're going to be using the rest of the semester as we head toward looking at population statistics. This unit, we're going to be looking at the building blocks of probability, and then going forward, we're going to combine these ideas with statistics. So today we're going to look at what exactly is probability, how to calculate and interpret it, the difference between probability and odds, and we'll finish up by looking at an example of something called a contingency table that comes up frequently in your homework sets. So, what exactly is probability? It's the likelihood of something occurring. Now, we're going to see how to use the formula in a moment, but keep in mind, whatever the problem is, if they're asking you for probability, the result is always between 0 and 1. So if you're doing a problem and the calculator gives you an answer of 5.3, definitely a mistake somewhere. The larger that value is, the more likely it's going to occur. So a couple definitions. An event is just any outcome of a procedure. It's what we're interested in getting the probability of. But we'll want to sometimes consider something called a simple event. And a simple event is an event that you cannot break down into different possibilities. So for example, if I roll a die and I consider the possibility rolling an even number, that's definitely an event. It's some possible outcome, but it's not simple because rolling an even number, I can break it down. It could have been a 2, could have been a 4, could have been a 6. Rolling an even number is not a simple event. But rolling a 5, that can't be broken down. That is a simple event. And the sample space is going to be a listing of all of those simple events in a procedure. So for rolling a die, the sample space would be 1, 2, 3, 4, 5, 6. Flip a quarter, it would be heads and tails. Pick a card from a deck, it would be all the individual 52 cards. Now there's two types of probability we can calculate. And the good thing is this isn't really something you have to worry about inside a problem because the formula is actually the same. But it really is where the numbers are coming from. In relative frequency probability, we're calculating probability based off data. So an experiment was done to collect those values. As opposed to classical probability, where there's not an experiment done, and instead we consider probability based on what could happen. We look at all the possible outcomes, and in classical probability, we do assume they are equally likely. But here's the formula. Whether it's from relative frequency or classical, the probability of an event is always going to be a fraction. The top number, the numerator, is always going to be how many times that thing happened, and the bottom number is going to be your total number of possibilities. The formula is that straightforward, especially in this homework set. You're really just dividing two numbers, but read the problem carefully. It's easy to make a mistake with these. So for example, 150 students are surveyed, 80 of them are required to take statistics. What's the likelihood that a random student takes statistics? Okay, it's a fraction. Top is going to be how many students take stats. The bottom is going to be the total. I read the problem carefully. Okay, 150 students are surveyed. That's my total. 80 of the students take stats. That's my numerator. It's going to be 80 over 150. I can certainly simplify that to 8 over 15. And if I want a decimal, I could divide and get 0.533. In general, probability numbers will round to 3 decimal places. But this is one to be careful about. When Mendel conducted genetics experiments with peas, one sample consisted of 428 green peas and 152 yellow. Based on these results, find the probability of a yellow pea. If I just go through this problem too quickly, I might say, all right, I know I'm dividing two numbers. There's two numbers. Let's divide it. 152 divided by 428, and I'll get the wrong answer. I want to read it carefully and see what they gave me. I'm looking for the likelihood of a yellow pea, so the top number is definitely the 152 for the yellow, but the 428 is not the total. It's just how many green peas are there. I can certainly find the total by adding them though. 428 and 152 is going to give me 580. So 152 yellow peas out of the total of 580. Classical probabilities, same idea, same formula with the fraction, just there's no experiment done. We consider what might happen. So one die is rolled, what's the likelihood of getting a 4? Top number, how many of those simple events give me a 4? Bottom number, how many simple events are there? I I'm rolling a die, so my simple events are the 6 individual faces. So the denominator is going to be 6, and of those faces, only one of them is a 4. Probability is 1 out of 6. Same idea, 1 die rolled. What's the likelihood it's odd? 6 simple events. If I think through those 6 faces, 3 of them are odd. My likelihood is 3 out of 6. I could reduce that to 1/2 or decimal 0.500, 50%. Now, one more definition. This one's going to become more important in the subsequent sections in this chapter because a lot of times what we'll find is we might have some complicated procedure we're trying to find the probability of, and it might be easier to look at its opposite, its complement. The complement of an event consists of all the outcomes where that event does not occur. It's the leftover parts. And symbolically, we'll usually write a bar above it. So E with a bar above it means complement of E. It means E does not happen. So card is drawn from a deck. Find the likelihood of not drawing the queen. So the top number, how many of them are not queens? Bottom number, how many cards are in the deck? Standard deck, 52 cards are in it. So denominator is 52. And if I think about it, if you know how the deck is laid out, it's 4 queens in the deck. So that leaves 48 cards that are not queens. And I could reduce that down to 12 out of 13. Now, this unit and going forward, certainly probability is the focus. It's what's going to give us the key to looking at population data. But odds are something that's very similar to probability. It shows up all the time in the real world. So we're going to talk about it briefly here and about the differences between probability and odds, because there is one critical difference between the two. Probability involves the total number of possibilities, but it doesn't do that with odds. With odds, you only consider how many times the event occurs and how many times it doesn't occur. And that's the numbers you're comparing to each other. The formula is that the odds against event A occurring, how many times it does not occur, divided by how many times it does occur. And sometimes you might see odds in favor of an event. In that case, that fraction would be flipped. And those of you who may have seen odds in the past, whether it's with the lottery, gambling, odds are typically given with a colon instead of a division bar. But that colon is actually holding the place of a division bar. It is still a fraction. So, example, 10 marbles in a bag, 3 of them are red, 4 of them are green, 2 black, 1 purple. Pick a marble. Find the odds against drawing a red marble. So there's 10 marbles in the bag. If we were asked for the probability of a red marble, the 10 would be part of the problem. It would be my denominator. But this is an odds problem. You want to be looking for these key words, and the key word here definitely is odds. I want to consider how many of them are red and how many of them are not red. 3 of them are red, 7 of them are not red. And this is odds against drawing the red marble, so the unfavorable goes on top. 7 of them are not red, divided by 3 of them that are red. And notice again, the result is 7/3, but we're going to write it with a colon, 7 to 3. I said that statement at the top that probability is always between 0 and 1. That's not going to hold true for odds. This certainly gives me a result that's greater than 1, but that cannot happen with probability. And we're going to finish things up by looking at contingency tables. Again, we're primarily going to be looking at probability based off real data. And contingency tables are just a way of organizing data into categories. So this is an example that comes up frequently in the textbook. It's a company that's doing a drug screening. So the employees in this company are randomly drug tested, and the results are summarized. So 2 things can happen. There's what the employee was doing, whether they use or do not use drugs, and then what happened with the test, whether it tested positive or tested negative. And one thing that's important, every single employee in this test falls into exactly one of these categories. So we're going to finish up by doing a problem with this contingency table. So using the table, find the probability that if I took an employee at random, that they test negative for drugs. So we still have that formula, that fraction. The top is going to be how many of them test negative, and the bottom is going to be my total. Okay, the total is going to be everyone involved in this survey. And I said every single employee falls into exactly one of these categories. So if I simply add up all the numbers in the table, it'll give me my total. Okay, 45, 5, 25, and 480 gives me a total number of 555. And then I want how many test negative. And this is the part to be careful about. That third column is testing negative. Some of the people in that column use drugs, some of them don't use drugs. But we don't care about that. It just said how many of them test negative. So it's the entire testing negative column. 485 people test negative out of that total of 555. So again, go through the problems carefully. If you have any trouble, if it's not matching, the answer is in the back. Reach out to me, office hours, the discussion board, class, so I can help you with it. Good luck.